what if the only way to save Earth was to blow up the asteroid that's heading our way? Imagine that astronomers discover an asteroid on a collision course with Earth. At first, there is nothing dramatic to see. No explosion, no glowing object filling the sky. Just a point of light moving through the darkness, following a trajectory that, according to the calculations, eventually intersects with our planet. And then comes the question humanity has never had to answer for real. What would we do? If the asteroid were small enough, Earth's atmosphere might protect us. If we discovered it early enough, perhaps a spacecraft could change its trajectory by a tiny amount, just enough to make it miss Earth. But what if the object were much larger? And what if we didn't have decades to prepare? Planetary defense is built around a surprisingly simple idea. We don't necessarily have to destroy an asteroid. We only have to make sure it doesn't arrive at the same place as Earth at the same time. That distinction changes everything. A spacecraft doesn't need to move an asteroid thousands of kilometers. A very small change in its velocity, applied early enough, can accumulate into a much larger difference in position over time. But timing is critical. The later we discover the threat, the harder the problem becomes. And that is why scientists have been studying different ways of changing the motion of potentially hazardous asteroids. One of those methods is no longer theoretical. In 2022, NASA deliberately crashed a spacecraft into an asteroid moonlet called Dimorphos. It was humanity's first full-scale demonstration of asteroid deflection. It worked. But DART also raised a much bigger question. If a relatively small spacecraft can change the motion of an asteroid, what happens when the asteroid is much larger and the clock is running out? That is where the most controversial option begins. What if pushing the asteroid isn't enough? What if we had to break it apart instead? On September 26, 2022, NASA did something that would have sounded impossible only a few years earlier. It deliberately crashed a spacecraft into an asteroid. The target was Dimorphos, a small asteroid moonlet orbiting the larger asteroid Dimorphos. The spacecraft was called DART, the Double Asteroid Redirection Test. DART was not designed to destroy Dimorphos. Its purpose was much more subtle. NASA wanted to know whether a spacecraft could physically change the motion of an asteroid. The spacecraft approached Dimorphos at high speed and struck its surface. Then scientists waited. The result was clear. Dimorphos's orbital period around Didymos became shorter by approximately 32 minutes. Humanity had deliberately changed the motion of a celestial body. For planetary defense, this was a historic moment. DART demonstrated that an asteroid does not have to be destroyed to be stopped. A small change, applied early enough, can be enough to alter where an asteroid eventually goes. And the impact revealed something else. When DART struck Dimorphos, it threw enormous amounts of material into space. That ejector produced additional recoil, increasing the effect of the impact. Later observations showed that the collision also changed the shape of Dimorphos. And in 2026, researchers reported an even more remarkable result. The impact produced a measurable change in the orbit of the entire Didymos-Dimorphos system around the Sun. The change was tiny. But that was precisely the point. Planetary defense does not necessarily require a spectacular explosion. It requires changing the mathematics of an orbit. DART proved that humanity can do that. But DART also tested a technique against a relatively small target. And that leaves us with the next problem. What happens when the asteroid is much bigger? And what happens when there isn't enough time to gently push it away? Asteroid defense is ultimately a problem of physics and time. The earlier an asteroid is detected, the more opportunities humanity has to change its trajectory. A tiny alteration made years or decades before a predicted encounter can become a huge difference by the time the asteroid reaches Earth's orbital neighborhood. But imagine the opposite scenario. A large near-Earth asteroid is discovered relatively late. Its trajectory is already well understood. Its size makes a small spacecraft impact far less effective. And there isn't enough time for a slow gravitational tug or another gentle method to produce the required change. Now the problem becomes much more difficult. This is where scientists begin considering methods capable of delivering far more energy to an asteroid in a much shorter period. The Chinese study that inspired this documentary explores precisely this type of planetary defense scenario. Published in Space, Science and Technology in 2026, the research examines nuclear-based approaches for dealing with large near-Earth asteroids under different conditions. The important word here is simulation. The researchers did not demonstrate this system against a real asteroid. They modeled how different approaches could behave and examined the conditions under which a nuclear intervention might become effective. The study focuses on a particularly interesting concept. Instead of simply treating a nuclear device as something that explodes on the asteroid's surface, the researchers examine a multi-stage approach designed to increase the interaction between the energy release and the asteroid itself. The objective is not destruction for its own sake. The objective is planetary defense. Either the asteroid could be substantially disrupted, or its trajectory could be changed enough to prevent a catastrophic collision. And suddenly the question becomes much more uncomfortable. If we discovered an asteroid large enough to threaten civilization, and conventional deflection methods were no longer sufficient, would humanity be willing to use the most powerful technology available to stop it? The idea of using nuclear energy against an asteroid sounds like science fiction, but the underlying question is scientific. A nuclear event can release vastly more energy in a very short time than conventional spacecraft propulsion systems can deliver. That makes nuclear methods interesting for a very specific planetary defense problem: a large asteroid, a serious threat, and limited time. The 2026 Chinese research explores this possibility through simulations. One of its central ideas is that the interaction between the energy release and the asteroid matters enormously. The researchers examine a two-stage concept in which an initial spacecraft interaction creates a cavity or opening in the asteroid, followed by a second intervention intended to couple more energy into the object. The goal is to improve the effectiveness of the nuclear approach, compared with simply detonating a device at the surface. But there is an important reason we should not describe this as a guaranteed solution. Asteroids are not identical. Some may be relatively solid. Others can be loosely assembled collections of rocks and dust. Their composition, internal structure, size, rotation, and trajectory can all influence what happens when they are struck or disrupted. And there is another problem. Breaking an asteroid apart does not automatically mean the danger has disappeared. If the resulting fragments continue along trajectories that intersect Earth, the situation could become more complicated rather than less. That is why planetary defense is not simply about producing the biggest possible explosion. It is about controlling the asteroid's future trajectory. The Chinese researchers' work is therefore best understood as an investigation into one possible high-energy defense strategy under difficult circumstances. It is not a deployed weapon. It is not a tested planetary defense system. And it is certainly not proof that humanity could simply destroy any asteroid heading toward Earth. But it demonstrates something important. Scientists are already thinking about what happens when the easy solutions are no longer enough. And that brings us to the most important question of all. Would such a strategy actually work when humanity needed it? This is where the story becomes much more complicated, because stopping an asteroid is not the same thing as destroying one. If an asteroid is detected decades in advance, the best strategy might be remarkably gentle. A small change in velocity could gradually move the asteroid away from its predicted collision path. DART demonstrated the principle experimentally, but if the warning time becomes shorter, the required intervention becomes more demanding. And if the asteroid is extremely large, the problem becomes even harder. That is why researchers study multiple approaches instead of searching for one universal solution. Kinetic impactors, gravity-based techniques, other forms of trajectory modification, and, under certain extreme scenarios, nuclear methods. The 2026 Chinese study contributes to this larger discussion by modeling how a nuclear approach could perform against large near-Earth asteroids. But simulations have limits. We have never conducted a full-scale nuclear planetary defense test against a threatening asteroid. We therefore cannot simply assume that every prediction will translate perfectly into reality. The physical properties of a real asteroid could differ from the assumptions in a model. Its internal structure could change the outcome, and the consequences of fragmentation would have to be carefully evaluated. This is why early detection may ultimately be our greatest defense. The more time we have, the less dramatic our response needs to be. A civilization that detects an asteroid decades before impact has options. A civilization that detects it only months before impact has a much smaller menu of choices. And that may be the most important lesson from DART and the new nuclear defense studies. The goal isn't to build a weapon powerful enough to destroy an asteroid. The goal is to develop enough knowledge, technology, and warning capability that we never have to make that desperate choice, because the best planetary defense may be the one we never have to use. For now, there is no known asteroid that requires humanity to launch a nuclear defense mission. The scenario remains hypothetical, but the threat itself is not imaginary. Asteroids have collided with Earth throughout our planet's history. We know that large impacts can have consequences on a planetary scale, and for the first time in human history, we are developing technologies designed specifically to change the trajectory of another celestial body. DART was the beginning of that practical demonstration. The mission showed that humanity can reach an asteroid, collide with it deliberately, and measurably change its motion. The new Chinese study takes the question into a more extreme territory. What if the asteroid is much larger? What if the warning time is shorter? What if conventional deflection isn't enough? Under those circumstances, nuclear technology could become one of the options considered by planetary defense researchers. But there is something even more important than the technology itself: detection, observation, prediction, preparation. Because the greatest advantage humanity could ever have against an asteroid is not a bigger explosion, it's time. Time to discover it, time to understand it, time to calculate its trajectory, and time to change that trajectory before Earth is in danger. One day, perhaps decades or centuries from now, humanity may face an asteroid that is genuinely headed our way. When that day comes, we won't have the luxury of inventing the solution. We'll need to have already tested it, because the question isn't whether we can destroy an asteroid. The real question is much bigger. Can we become a civilization capable of protecting our planet before we need to? If you want to explore the science behind humanity's efforts to defend Earth from the dangers of space, subscribe to PointView. Because the next threat from space may not announce itself until it's already on its way. And the future of Earth could depend on how early we see it.